You're the ones Evan was talking about. And you want to learn more about packed columns? Well, I've got the thing for you.
By now, I bet you already have a basic knowledge about packed towers. So just to recall, a packed column consists of a column with inlets for liquid and gas at the top and bottom respectively, and outlets for liquid and gas at the bottom and top respectively. The column is filled inside with inert solids called tower packings. The inlet liquid, which may either be a pure solvent or a dilute mixture with the solute, is called a wick liquor. As it leaves the tower, it has already absorbed the solid particles from the gas stream, and the exiting liquid stream is now called a strong liquor. If we were to open a packed column, what we were mostly about to see were the following: the tower shell, which is the body of the tower, a mist eliminator, which is used to prevent liquid droplets from exiting the absorber with the gas stream, packings, which will be discussed further later on, and then we also have distributors, which help spread the streams and provide better contact between the liquid and gas streams. There are also support plates inside the packed tower, which are usually made of screens with a large open area so that flooding does not occur. And then lastly, we also have redistributors, which are used to introduce and or to mix liquid at regular height intervals. So after discussing the parts of the packed tower, we will now proceed to perhaps one of the most unique part of the packed towers, which are the tower packings. These packings are used to provide a larger surface area for the contact between the gas and liquid streams. Depending on the type of streams to be used, different materials per packings may be used. Plastic ones may be used if a lighter weight is desired. Ceramic ones, on the other hand, is used for streams that may cause corrosion. According to Paris Chemical Engineer's Handbook, packings can be classified into three: random or dumped packings, structured or systematically arranged packings, and grids. The first type that we are about to discuss is the random or dumped packings. These are solids of specific shapes that are randomly placed into the column shell. Here is an illustration of the commonly used random packings: Rashid rings, Paul rings, Pearl saddle, and interlock saddle. The second type of packings are the structured or systematically arranged packings. As what you can see from the picture, these are made of print layers of corrugated sheets or wire mesh. The last type of packings are the grids. Grids are somewhat the same as systematically arranged packings, but instead of mesh or corrugated sheets, these use an open lattice structure. The most common type of packings in commercial use are the random and structured packings, while the application of grids is primarily limited to heat transfer and wash services where a high fouling resistance is required. So what are the characteristics to consider in choosing the appropriate packings? So first, we should consider the wetted surface area for phase contacting. And then related to this is the void volume, or the space where the streams could sit in. And then we should also consider the wetting characteristics. So another factor that should be considered is the reactivity of the packing with the streams, especially if corrosion may occur. And then another factor to consider is the bulk density and also the cost. So generally, we use packings to maximize the efficiency by providing a good surface area for phase contacting and economic cost. So to achieve the goals of packings, these solids are shaped so as to, number 1, provide a large surface area for phase contacting. Number 2, spread the surface area uniformly. Number 3, maximize the void space in the column. Number 4, minimize friction. And lastly, to minimize costs that will be used for the absorption. Now that we already have a deeper understanding of packed columns and tray columns, how would we know if we should choose one over the other? So generally, the decision is based on the characteristics of the fluid or streams to be used. Perry presented conditions that were favorable and unfavorable for packed columns. Packings are generally cheaper than plates, especially if small columns were to be used. Also, trays are usually made of metal, so handling of materials that can cause corrosion is not possible. However, due to the existence of ceramic packings, packed columns can handle materials that can cause corrosion. Efficiency is affected by pressure drop inside the column, and packings exhibit desirable effects in pressure drop. Another factor favorable for packed columns is the way it handles foaming. Packed towers can handle foaming because of the relatively low degree of liquid agitation by the gas. Also, holdup of liquid can be quite low in packed columns, an advantage when the liquid is thermally sensitive. Now for the conditions unfavorable for packed columns. Plates are comparably easier to clean than packings. Due to its size and material, packings can easily be broken due to insertion or due to thermal effects. There also is a limit in the velocity of the liquid that packed columns can handle, so high liquid rates cannot be handled in packed columns. To reduce thermal effects, tray columns offer devices such as cooling coils. The low liquid rates in packed columns may also result to incomplete wetting of the packings, and thus decreasing contacting efficiency. So I have mentioned earlier that there is an upper limit of the liquid rate that can be handled in packed columns. Well, there also is a limit for gas rates as well. This upper limit is called the flooding velocity. Since above this limit, flooding in the column will occur, and the tower cannot operate above this gas velocity. At the flooding point, the liquid can no longer flow down through the packing and is blown out with the gas. As the gas flow rate increases, the pressure drop also increases to the 1.8 factor. Another problem encountered at high gas velocities occurs at the loading point, where the liquid downflow is hindered by the gas. At these loading points, accumulations or pools of liquid start to appear in the packing. It is important to know that as the gas flow rate is increased, accumulation or liquid holdup in the packings also increases. Since flooding or phase inversion normally represents the maximum capacity condition for a packed column, it is desirable to predict its value for new designs. Different methods for determining the pressure drop at the flooding point can be used, but one of the most commonly used methods is by using the generalized pressure correlation. The parameters for the generalized pressure correlation are the following. Rho refers to the densities. Ft refers to the packing factor, which can be found in tables 14-13 and 14-14 of Perry 8th edition. V is for kinematic viscosity of the liquid, and Cs is the C factor. which is based on tower superficial cross-sectional area. The departure from uniform distribution of the faces in the packed column can be caused by the following. First, by the malfunctioning of the liquid distributor. Second, the liquid moving easily to the wall than vice versa. Thus, the resultant channel